today will be devoted to proving the following theorem, and this is a special case of Margulis rigidity. But it is a special case, but it contains all the ingredients. So somehow, I think. Yes. So it contains all the ingredients, but somehow maybe it's easier to see. And I won't even state the general form. It's available in many books. And so I will have a target group, which is SL3R. This could be generalized for SLNR or any simple group, but the rank should be 2 and higher. If you're not familiar with this, SLNR with N 3 or higher. And the theorem concerns lattices in subgroups. So an arbitrary lattice gamma. An example would be SL3Z, of course. And we will have an algebraic group, which we'll take here to be a complex algebraic group, and they want to be simple. So if we see in our discussion, theorem holds also for other fields, but I will not discuss this one here. It's not so hard to extend. One remark that I already want to make is that we will use results that I said in the, of course, all through this lecture series. In particular, yesterday I discussed a simple group, and I took SLNC. But just a remark that SLNC itself is not simple. It contains a root of unity of order n as scalar matrices in the center, so you should divide it up. Whatever I said yesterday about SLNC, I should have said about PGLNC, which is SLNC modulo center. This is not a big deal, just there was a slight mistake there. And now the data of the theorem is a given homomorphism, group homomorphism from gamma to this unknown G. And the assumptions are that this is a risky test and unbounded. Unbounded. So the image is not rectangular. And what the theorem says, then one can find an extension, rho bar, from S, the mother of gamma, to G, such that rho is just the restriction of rho bar to gamma. A remark, it follows, now since S is mapped the risky densely into G, it should follow from that that N is 3. This is just a tiny remark that I can make, but it's not of interest now. Okay, so we'll devote this lecture towards proving this theorem. It has many applications. This and its other versions have many applications. And the idea, one, so
Regarding the statement, are these just abstract homomorphisms also?
Rho is an abstract homomorphism. Gamma has no further structure. It's a countable group. So Rho.
The lattice closed and the rho bar is also an abstract.
Rho bar will be actually. Okay, this is a general fact that any map, any abstract homomorphism between such group is actually algebraic. This is what will follow if we look very carefully on the proof. I will not emphasize that. That will follow that rho bar is continuous and actually algebraic. This could be further achieved by studying abstract homomorphism between such groups. There is a whole theory of Borel tease about this. Abstract homomorphism between algebraic groups. But I will not discuss this parenthesis line, but this is just for your okay, so obviously we are about to use ingredients that we've seen. What is the new idea that I want to add, and what is special about SL3R, which I emphasize that we are using higher rank. The higher rank property of SL3R reflects by I'm not sure my English is very well, very good. In having in SL3R, I will use having 6 unipotent groups, 6 nice groups that well, together they generate SL3R. And of course, they cannot all commute, since SL3R is not commutative, but they do commute in successive pairs. Let me be specific about it. Let T1, I'm now defining the 6 groups. T1 is that group. Whenever I'm not writing something, these are zeros. It commutes with this one. T2, sorry. T3 will be that one. If you probably you are familiar with the fact that T1, T2, T3 together generate the Heisenberg group, and T2 actually is the center of the Heisenberg group, is the commutator of T1 and T3. So in particular, T2 commutes with T1 and T3. Up to a change of coordinates, also T2, T3, and T4. This playing with some permutation of the lines and rows, and see that this is an Heisenberg group and T3 is the center of that one. T5 is the center of the lower Heisenberg group, and T6 would be, I guess, this one. Also T6 commutes T1. There is a circular. It somehow reflects the, if you are familiar with root systems, it reflects this A2 nature of the root systems, but you don't have to be familiar with anything in order to understand this. This is very standard. You can check commutation if you wish. All TIs are non-compact. I will use these. It's obvious what I'm writing it. They are closed subgroups which are isomorphic to the real line. They are non-compact. They are abelian each, so they are in particular amenable. And this came in our discussion yesterday, so I'm emphasizing that one as well. Ti commutes with Ti plus 1, actually in cyclic order, and together they generate S. So S is far from being commutative, but somehow it's locally commutative. And this is, I didn't define this notion. Let's not regard this as a definition here. It's this property for us. It could be generated by commuting big groups, successively commuting. Okay. Let me now something we've seen yesterday. There exists H, which is not all of G, and this is, it appears very, a small sign here, but this is, emphasize this, proper sum of EG, proper algebraic subgroup. And a representation and an algebraic representation let me focus now, maybe let's take T1. This is a non-compact amenable group. So if we take S mod T1, our space X, and consider the gamma action on this one, and rho, the one there, 2G, we prove this existence, right? So what we proved, we proved that always we have some minimal guides like that, and what we worked using amenability of T. What we worked in order to prove is the non-triviality of this H. This was the last hour of technical symbols on board. So this is important. This will be used. But now I want to state it differently. What I want to achieve now is a homomorphism from S to G. In my mind, taking this point of view, S is a measurable space. S, I don't think of it now for a minute as a group, but as some Lebesgue space acted upon by gamma. Okay? The action of gamma alone on S is not ergodic, of course. It has a nice quotient space, which is S mod gamma. But gamma times T1 do act ergodically on S. So let me rewrite this one with this in mind. So equivalently, I'm rewriting this diagram in a more complicated form. Take S, act on this one by gamma times T1, and map this into G times the trivial group here. This would be rho times the trivial map. And this act on G mod H, this reflects the fact that T1 acts trivially. This is basically phi composed with the map from S to S mod T. Right? And now, it would be very nice if I could show that this H is trivial. Then this phi, it's not a group homomorphism, but it has nice equivariancy properties already. If H was a group homomorphism, this will be an approximation of this rho bar that I'm looking for, right? But there is no reason for H to be the trivial subgroup of G, and it need not be. But somehow I use some very stupid map homomorphism, tau, the trivial homomorphism from T1 to a trivial group. Let's try to, and the trivial group acts trivially on this. But we know that in general we have a larger group acting here if N is the normalizer of H. Or this one does act here. Maybe I can make better if I will try to map T1 here into this group and get better results. This is the idea. And so somehow I want to encode this into a new theorem I'm about to develop, which will be slightly technical to formulate, but but very naturally in this context.
So gamma doesn't commute with T1, so...
Yeah, gamma does commute with T1. I should emphasize that. Gamma acts on the left, T1 acts on the right. On S. So you do have commutation. And actually, and this will come later, also T2 act on the right, commute with T1, obviously commuting with gamma. So we have some extra commutativity here that we haven't used yet, but we will use later. So, can we make it better?
I wonder, when you say that gamma acts on the left and T1 acts on the right on S,
Yes.
then what action is of gamma cross T1? Gamma cross T1 is a group.
Gamma cross T1 is a
And
group.
then you say that it acts on S.
Yes, by the left action of gamma and the right action of T1. Whenever two groups act commutatively, in commuting manner on a set, then the product group does act as well.
Yes, but in usual terminology, we distinguish when we speak of an action of a group on another set, then we either say left action or right action.
Or if you want, okay. If you want to be super formal, I don't think there is, but you can think of S as identical as an S space. Or,
Both are left actions. One is by left translation, and the other is by inverse of right translations.
correct. When I write this, I view both as acting on the left, but the way the action is formulated is indeed, for T1 is by right translation. You may identify S with S times S modulo diagonal.
It's just too hard to say it.
And then this is just the left action on S times S. Okay. Okay, so this discussion motivates the following definition, which might, okay, maybe find a better map. T1 to L, or T1 to here. This is somehow how I want to think of it. And now, this idea comes into the following definition, which is by representation reps of by actions. We discussed last time representations of actions. Now I want to view S as a by action of gamma times T1, but they are not in equal, there is no symmetricity between the two. Because for gamma I specify the map to G, and for T I want to find another map, theta, into some other algebraic group, which is not part of the fixed structure. So now I want in my mind to fix some structure and to vary other. So please stay focused. A birep of the bi-action gamma times T1. Maybe I'm switching to more general. I kind of fix some of my specialized notation, but try to free the discussion. So by action is just a commuting action here, but I want to emphasize this because by representation, I will not just regard this as product group acting and study representation of the product group. I will use in what follows the by action in a non-entirely symmetric way. So this is given. Here I have like the symmetry. This is part of this G fixed algebraic group. So part of my fixed structure is that action, that algebraic group, and that homomorphism. This is Z dense. Is, and now comes a list. An algebraic group L and a homomorphism dense homomorphism theta T to L. So this, here I break the symmetry, this is not part of my fixed structure. This varies. G times L variety. So G times L do act on V. And lastly, rho times theta map X to V. And map is here with all the adjectives. Rho times theta means the following. Let me repeat. We have gamma times T acting on X. We have here the map rho times theta. We have here G times L, and it acts on V. And again, you should think of G as a fixed guy, L as a varying guy, rho fixed, theta varying. And this map phi should be, as usual, a map between the Lebesgue space X to the Borel space V. So it's Borel, measurable, almost everywhere defined. And we think of it up to niceness. And it should commute with the gamma times T action on X and V. Okay, so this is the structure. This is a new object in a new category. Slightly more complicated than one we've met before. But not too hard to understand. Now, of course, I need to define for you, in order to argue about to define a category. As I mentioned, I am about to argue that there is an initial object in that category. I want to study it for this specific setting that we have over there. That appears naturally in Margulis superrigidity. I want to have an initial object. I want to define morphisms. To define morphism, if you think about it for a while, you will find the right notion of morphisms. There is one obvious definition. When I'm about to write down, it might appear a bit complicated, I don't know, but so you will just have to accept it.
To the main formulation of the main theorem, because this says about the extension of a given homomorphism law.
So you're asking a question which is not related to any of these three.
About the first theorem.
So we are coming back to the first 5 minutes of the talk.
Yes.
So sorry for breaking this discussion now.
Sorry.
But let's.
But where does this super-rigidity term come in with this formulation? Because rigidity is like non-existence of an automorphism.
So not over that if G is not precisely PGL3C, if G is not that specific one, there are no homomorphism from S to G, hence no homomorphism from gamma to G. So this is a very strong rigidity statement. Furthermore, it is super strong in the sense that if G is what it should be, then all the actual homomorphisms are coming from a very restrictive family. So this is super rigidity. And not to prove this, we're developing this theory. And now I want to define, or maybe, let me add one more line. Briefly, for short, I would probably use the following short notation. The bi-rep is just denoted, as we do many times, by V. I will say that V, or sometimes phi, is a bi-representation of X. Implicitly having all the other structure here. Denoting, if I'm doing it, I will denote L sub V, theta sub V, phi sub V, according to this choice of letter V. Okay, that's how we think of things. And let me already use this notation by defining a morphism. A morphism between the bi-representations phi u to u and phi v to v, with all this extra structure, of course, that I'm hiding, in particular with different L's, those to come. Is a G times L morphism U to V where L is now defined, I haven't defined it yet, to be the theta u times theta v of T. There is a closure inside Lu times Lv is acting, so this is a definition, is acting on U and V via the projection or the restrictions of the projection. We have obvious two projections to Lu and Lv. And now let me write it in the dramatic way. It's a bit cumbersome. We have maps from X to U and to V. We have gamma times T acting here. We have G times Lu acting here. We have G times Lv acting there. We have these maps. Let me write all the data. Rho times theta U, rho times theta V, phi U, phi V, sorry for being boring. And now, on both these spaces, we have actually an action of G times L, and we have these maps. And we have this now new map, all times in theta. And what I'm asking now is this psi, commuting with everything. Okay? So it's a complicated diagram, but this is the natural notion of morphism that one comes with. Any question?
What would happen if we skip the right G cross L and instead put an arrow, a vertical arrow?
Between this one and that one? Actually, this is a good question. In our notes, when we first wrote it, this is how we had. You should, but sometimes, maybe, so what happens, maybe this action of Lu, maybe it will have some kind of, you should think about L as some sort of inflation of Lu. Maybe you want to allow a bigger group acting on U with some kernel here, and this bigger group to map to Lv.
Is this equivalent? Or?
No, this is not equivalent. This is the right formulation. I don't want to open this discussion right now. We're happy to talk about it in the break, but this is a mistake I've done. So. So I'm not sure this is a good question, but it's certainly.
I mean, this is like a natural notion from
Yes. Yeah, but so somehow this, I'm allowing some inflation of the acting map LU before mapping into LV. I'm allowing some, to add some kernel to that. This is the heart of this slightly more complicated than we needed definition. Seemingly more. Any more questions? So at the remaining of this first hour, my wish is to prove the following theorem. Or maybe I should say, this is very general, and if we try to prove the theorem that we see an analog to the theorem that we had yesterday, that in the category of representation of an ergodic action there is always an initial object, we will fail. In order to understand this, we should maybe briefly recall the proof. Now, forget this complicated setting for 1 minute. Remember the more naive definition of representation of one action, of an ergodic action. Somehow we had an initial object of the form G mod H, where H was some minimal subgroup existing due to the theorem property that accept, such that G mod H does accept a representation. And then we had some diagram showing that this actually holds, I mean that this will be an initial object, but the definition of H was using Noetherianity in the space of all subgroups of G. Somehow whenever G acts on a variety V, and we have an ergodic measure on it, it is focused, it supports only one orbit, some G mod H, and we were looking for such a minimal guy. Now if G times L acts on a variety, supporting some ergodic measure, then this will be supported on some orbit, but it will be a G times L orbit. And L is arbitrary. So somehow I have a problem of taking a minimal object in a subgroup of G times L when L varies. This is my problem now. But what will happen is that if I will not consider the general category for general X that appears here, maybe I should have asked to this term. But there should not be an initial object to that category in general. But yes, there will be in the specific situation that we are dealing with, and this is due to the weak mixing of T1 on S mod gamma. Due to the How-Moore property, due to the things that we've seen, metric ergodicity, whatever you call it, T act not only ergodic on S mod gamma when S is SS3, T act doubly ergodic. T act weakly mixing. And we know that weakly mixing dynamics have no trace in algebraic geometry. This we've seen yesterday. Okay? Due to this fact, when we have this extra ergodicity, which I'm not trying to encode into the general definition, now, we will have an initial object. So instead of trying to axiomatize when this is the case, let me now move and discuss that example of interest for us. The action of not general gamma times T on X, but gamma times 1 of the Ti's on that specific S, which is, this will be my X. So here I'm saying here, for X, which is S as a vector space, it's that group with the How measure, gamma inside S lattice, somehow in my mind when I write S, I think of the group. When I write X, I think of the space. T in S non-compact and for the natural action, left and right action, of gamma times T on X, and a given rho, and this should be, this would be T, G, L, N, C, and this is Z dense. Actually, I don't need unbounded at this moment. Under this setting, for this specific data, putting this into the definition of by action and by representation, there exists an initial object as before. There exists G, algebraic. L acting on G mod H, but it will act on the right hand side. So there will be some specific L inside here, algebraic. Theta from T to L, Z dense. And finally, maybe Phi naught. From G mod H, such that all these data form an initial object in that category of discussion. Is an initial object. Gamma times T on X with respect to that given object. Okay? So this is what this is the proof I owe you now. I hope this is understood. This is similar to what we had before, and let me be sketching in the first one. Maybe let me try to describe what I want to do, to describe again. I already started doing, to describe what fails, and to describe how to fix it. Maybe fixing, maybe leaving some details to you guys. I would like to a formal proof, but really I want to have this picture that we had on the board somehow given, let me remind you, given x to v with some decoration. We need to find G mod H to v, or maybe as with all the decoration, and G mod H is, we need to define it. It should be given at the term. And of course, here there should be some G times L action, and this should be G times LV. And this L is the L appears there. L is in the normalizer model range. Something like that, for short. And how did we try to do it? So we choose H minimal in all H's in G, such that there exists something of this sort, direct, with all these extra words, and consider the following complicated thing. And consider such a thing. So we have V, we put now G times H on the other side, we have X mapped to this, and we want to connect them with that arrow over here. What we have done before is to consider this guy in between, to consider projections, and to say, hey, but if X mapped here, X mapped there, then X is mapped here by diagonal action, by the product map, but X is ergodic. Everything here is gamma times T maps. Right? We have gamma and T in the back of our mind. I'm not denoting them. I'm not putting them on the picture, but they live. And X is gamma times T ergodic. It will hit one orbit here. Right? But what kind of orbit? It will be some, well, actually, which is the group that act here? Here I have action of G times L. Here I am having action of G times LV. Here I'm having action of G times L times LV, or some group in that product of L times LV, which is the image, the Zariski closure of the image of T. And in any case, so I will have some L prime acting here. L prime is, let me find this, if I'm doing it, theta V times theta with no symbol is theta given from that structure, T Z inside L times LV, times L. So there is some group acting here. I denoted it L prime for a minute. And what Ergodic gives me is some G times L prime modulus some other guy, M, in here, that will receive X. And somehow this is not good enough for me. This is where I find myself not being able to proceed in the proof. I hope I'm being clear. What I want to establish now is that this is actually isomorphic as a G space to G mod some H prime. I want to show that actually G does act transitively here. And if this is the case, if the action here is actually transitive, and this means that L prime is actually acting on the right-hand side via mapping to normalizer, etc., then I could again do this, observe that, go here, say, okay, we have a map. Right? So my problem is lying here. I want to finish this small discussion before the break. So I'm just going by a tiny bit. So let me state now a lemma. Under the condition of the theorem. And the definitions we see here, maybe should be here, for every direct x to b. Again, these are the general definition, but the lemma is under the condition of the theorem, under this special setting, which I'm not writing again. There exists G times H prime, gamma times T, 1 times theta, or maybe, okay, I will continue. So maybe I'll just restate the essence of what I need. Excuse me. For every birep of the kind here, x to G times A prime mod M, and this is gamma times T acting on X, and this is G times L prime acting here, and this is rho times theta prime here. The space G times L prime mod M is G prime. And now, since my lack of time, since I already explained, I think, most of the things, I leave it to you to complete. I will prove the lemma, but I leave it to you to complete the proof of the theorem given the lemma. Okay? It's observing this diagram, and if you don't remember it by heart, reading again what we've done here. And the proof of the lemma is quoting weak mixing. Let me do it very briefly for you. So I'm looking at this G times L prime mod M, and let me now divide by the G group action. What is the space of orbit with respect to the group to the G action? I claim in this is L modulo the projection of M to L. So M is a subgroup of G times L prime. I have a homomorphism here to L prime. And I can, this is P2, and this is P2N. It's a closed subgroup. Why closed? It's not a general fact that it is closed. This is because we are lucky enough to live in algebraic domain. Okay? So this is a closed subgroup, and the G action here is trivial. Remember, G was acting here on the left, and actually it was reminiscent of the gamma action here. So this map from here to here is gamma invariant. Right? You have always X, let me call it S again. We have always S mod gamma. And by gamma invariance of this one, because gamma acts through G, and G doesn't act here anymore, this map factors through that. And now T here is double ergodic, or weakly mixing. Weakly mixing. This is double ergodic PMP action. And we've seen what we've seen. Look at this last line and think of this. Just a minute. T is mapped into L prime. This is theta prime, right? And L prime act here. Think of this last line as an algebraic representation, not by representation. Just an algebraic representation of T acting on S mod gamma. We've seen that the initial object of these guys is trivial due to weakly mixing. Or we've seen that this cannot support any weakly mixing measure unless they are delta measure. We've seen weakly mixing measures on algebraic variety are delta measure. Right? This is one of the things that we've seen yesterday. This means that the image here of S mod gamma is just one point in here. And this point is just, it's not just any point. This point is gamma fixed point. Inside this variety. Inside L prime mod P to N. If point is, so T fixed, see this. This is a T covariant map. Constant T covariant map, and the map is T fixed. Right? If a point is fixed by a group, acting algebraically, then the point is also fixed by this Ricci closure. I should have said maybe theta prime T fixed. And it is fixed by this Ricci closure. What is the Ricci closure of theta prime T? This Z dance that appears there, I guess. By assumption, the maps, my homomorphisms into algebraic groups are always risky dense. So please. Shout, thank you. This is L prime. And L prime this is a coset space. There is no L prime fixed point here, unless this coset space is trivial. This group is L itself, L prime itself. This space is just a fixed point. And to say that this space is a fixed, is a point, is to say that G was acting transitively here. Right? So using weakly mixing, we show that G was acting transitively here. And we can replace that space, actually here, this G transitive space, by a G coset space, on which L prime still acts on the right? But, and repeat the argument we had before. Altogether, this gives a proof of that term. And this term, again, stating that in some very specific setting, with the existence of some weakly mixing property, for that category, general category, we have initial objects. And this, together with commutation here, an ability somehow of replacing the role of the T's, will serve us in the next hour to prove that. So let's take a break.